Hello everyone, I'm Chanchal. Uh, Welcome to a new lecture on MOSFET circuit simulations. In this video, we'll look upon simulations of circuit MOSFET circuit, not amplifier, only switches and variable resistor. So first we'll be looking upon introduction, VA characteristics of NMOS DC circuit and comparison with NPN version of it, NMOS LED driver, PMOS DC circuit, NMOS source follower, NMOS analog switch, NMOS variable resistor. So both the lecture, it's a theoretical and practical kind of lecture. It's levels BTech. As a reference, I had taken from microelectronic circuit, Sethran Smith microelectronic circuits. Prerequisites are engineering mathematics, network analysis, electronic circuits, solid state devices. We will not go into deep into solid state devices, but you will be looking upon only on circuit and its simulations on TINA. In the last lecture on DIAC and TRIAC, we have visited TINA, so you may be familiar with that. So introduction. So what is MOSFET? It's a transistor used for amplifying or switching electronic signals. Unlike BJT, it's a voltage control device. BJT was a current control device, and now MOSFET act as a voltage controlled current amplifier. That is if you look at the H parameter circuit, you will get that the model is just like voltage controlled current amplifier, but BJT is a current controlled current amplifier. MOSFET has its own advantage while designing a switch or logic gate. It has four terminals: gate, source, drain, body. Body is just to remove the electrostatic charges on the MOSFET transistor. Mainly, it has three terminals: gate, source, and drain. Gate is the input terminal, source and drain are the output terminals. It has two types: NMOS and PMOS. Where NMOS is a N-channel MOSFET, PMOS is a P-channel MOSFET. Where in NMOS the channel consists of electrons. PMOS it consists of holes as the channel. It has two types for NMOS and PMOS, and enhancement and depletion type. We'll be looking upon enhancement type. In all the microprocessors and all the ICs, most of the ICs they use enhancement type NMOS and PMOS, and the advantage are the high input impedance, so it can be used as a very good amplifier, because in amplifier we have to interface two circuits there, so it is easy to when it has a high input impedance, it can be interfaced to any circuit, any output of any circuit. And the second advantage is low power consumption. Mainly in smartphones and smartwatches, we need a low power consumption circuits, and that it is made up of MOSFETs, and MOSFET helps in making a low power devices, low power circuits, low power systems, and next advantage is scalability, where many MOSFET can be confined in one chip. Millions of transistors, more than BJT, and more than a number of BJT. Many times the number of BJT can be accompanied in one IC. Many MOSFET can be confined into one IC. And next is uses digital switch. Again, I told you in the microprocessors and all the phone, smart watches, any digital device you take, it has MOSFET. And now latest technology is FinFET. Many types of MOSFET are there. Mainly if you study the VA characteristics of MOSFET, you can study any type of MOSFET after that. So basically, digital switch means logic gate. Any gate, all the gate are made up of MOSFET, basically from inverter and NAND, NOR, any type of logic gate. It can be easily fabricated also, unlike BJT. Next uses power switching. It can be used. It is used as a power converters. It is used in power converters. where it can be used for hyper applications where high current are taken from the circuit. So that is a second use of MOSFET. It can be used as a power converters like buck and boost converters, and any for like in UPS and all. It can be used as a power MOSFET and in amplifiers in the power amplifier stage of amplifiers. It can be used as a yeah, the MOSFET can be used in that circuits. And next is amplifiers, like in RF amplifier, any audio amplifier, any it can be the noise is very less. Unlike in BJT, the noise SNR, the noise figure and SNR is very improved in the MOSFET. And next use is variable resistor. It can be the upon giving some voltage, the resistance of the channel can be controlled. So it can be used as a variable resistor, just by giving the input voltage and varying it. It can be the resistance of the channel, that is the drain to source channel can be resistance of the drain to source channel can be varied. And that's a very important application. The BJT has no such feature like that. So this is a add-on use of MOSFET. Now let us see the VA characteristics of MOSFET. The main first condition is to turn the MOSFET on, or to just pass current to the channel. The condition is VGS is greater than VT. So it has a threshold voltage. After below that, it remains in cutoff. As you can see here, this is a cutoff region. This is a VA catalyst. The VGS, this is a VDS on the x-axis and ID on the y-axis. So below VGS equal to 0 volt. It's a cutoff region, and it has three regions. Ohmic and other regions are ohmic and saturation. Ohmic is also called as triode region. So when VDS is less than VGS minus VT, this VGS, this is an important equation here to discriminate triode and saturation regions. The VGS minus VT is oftenly called as overdrive voltage. So VDS, when VDS is less than the overdrive voltage, it remains in ohmic region, and this two regions it act as a logic gate. It used in logic gate. This MOSFET act as a logic gate in this two region. That is in ohmic and cutoff region. In saturation region, the main application is it act as an amplifier, any power amplifier or any voltage amplifier, such as in audio circuits. It act as an amplifier, audio amplifier. That is it remains in saturation region. All the amplification take place in saturation region. So that is the condition is VDS is greater than or equal to VGS minus VT. So in this region, you can see this blue line, blue dotted line. In this, this is the pinch off region of all these VGS voltages. And after this pinch off region, it enters into saturation. Before that, it goes to ohmic, and for to act as an amplifier, it remains in the pinch off region. Okay. We'll not be discussing about the solid state characteristics of the MOSFET because we will be dealing only circuits. Okay. So there are 6 circuit here. So this is the first circuit, NMOS DC circuit versus its BJT version. This is NMOS circuit. This is NMOS taken 2N675 as a MOSFET, and here I have taken the BC547, the popular BC547 as a BJT. And there are 2 resistors here to control the input and output current of the transistor BJT. Here it is this is a base resistor. In the color resistor, first we'll be designing the color resistor according to I taken here 5 milliampere from the equation VCC equal to ICRC plus VCSAT. VCSAT I taken 0.2. From here for 5 milliampere I designed this color resistor R2 1K. Okay. And input circuit, the base circuit, I taken for a gain of 100. I taken the base current, and from 5 volt. I have taken again from the equation the VBE equal to VBB equal to IBRB plus VB. VB is a saturation voltage. I have taken zero point 0.7 volt. Okay, so that is the thing here. And here we from the circuit, the output circuit, the drain circuit, I have taken VDD equal to IDRD plus VDS. VDS will be very small. When the channel is on, the VDS on resistance will be very less. So I taken 0 here, and taken some drain current here. So you can see here 5 by 10k, it is uh, 0.5 milliamp or 1k 1 milliamp, close to 1 milliamp, 0.5 milliampere. Okay, that is enough here. Okay, I take, and this the base voltage I have taken directly to the gate circuit, gate input. And there is no need of any gate resistor because here this gate acts as an open circuit here. There's high input impedance so in mega ohms. So there will be no gate current here. Gate current is 0. It acts as an open circuit here. So that's a very good advantage of MOSFET when interfacing to microcontroller circuit, microcontroller output ports. And these two circuits can be interfaced to output port of a microcontroller for switching application. Yeah, we had discussed in the earlier lecture how to design this BJT circuit, switch circuit. Okay, so now let us go into the simulation of these two circuits. So these are the two versions of the transistor circuit. This is BJT version, MOSFET version, and this is a color resistor, a base resistor. Here we have only a drain resistor because input impedance of the MOSFET is very high. No need of resistor, no input current, only voltage. So let us see the waveforms of BJT. So okay, see here. So it is gradually decreasing the voltage, or the current is gradually increasing. It's gradually going from off state to on state. This is on state of the BJT in saturation. This is the cutoff state. Okay, so when the input gradually increases, the output also gradually decreases. That is, it current increases and when it turns on. This is saturation voltage here, around 1.2 volt. It goes completely into saturation, or 2.2 volt or 2 volt. Okay, also okay. Now let us see the waveforms of MOSFET. It is entirely different. See here, just like a square waveform. The voltage, when the input voltage gradually increases, and only after a threshold it turns on. This is the on state of the MOSFET, off state of the MOSFET, cut off to triode. Okay, so this is the when it reaches the triode region, turns on. See, it turns on completely. It's zero. The output voltage is zero. This is output voltage 5 volt. So that's the advantage of MOSFET or BJT. Can be fastly switch over. See, because it depends upon the voltage. That's why the behavior is like that. Behavior is like that. Okay. So this is a waveform. It turns off to on suddenly, and on to off suddenly. Unlike BJT, which goes gradually. Okay, because it depends upon the threshold voltage. Above the threshold, it turns on. Below the threshold, it turns off. That's why the behavior is like this. Okay, I think you have got it. You have understood. Now let us go to the next circuit. Circuit 2, NMOS LED driver. This LED driver can be connected to a output port of a microcontroller. This transistor NMOS MOSFET is needed to drive the LED. Okay, so given we have taken is 2N675 as a MOSFET. This is an LED, green LED, and I have taken 330 ohm resistor here, 330 ohm resistor. And the equation is VDD equal to IDRD plus VD. VD means this LED, VD or diode or LED, VLED voltage. Okay, and this will be 0. And when on the on condition, this MOSFET act in the triode region. Okay, here the 5 volt is the output port of a coming from the output port of a microcontroller, usually 5 volt TTL, or otherwise it can be also connected to 3 volt microcontroller port. Okay, so I given ammeter to measure the current. This is the 5 volt VDD. I designed this resistor for 10 milliampere, so 330. VDD 5 equal to, we have taken 2 volt, 5 equal to 3 ID RD at ID into the 330 by plus VD plus 0. So that will become 10 milliampere current, or approximately 10 milliampere or 9.9 milliampere. Okay. So now let us see the simulation circuit. So this is NMOS LED driver taken transistor 21655. This is the output port where it is it's open circuit here at the gate. Okay. So now let us see the voltages. VM1. See, oh sorry, it's oscilloscope as multimeter voltage. Just let us see VM1. So here it is very almost zero voltage because it is taken across the VDS, and here the condition is VDS is less than VGS minus VT. That is before the pinch off. It is in the ohmic or triad region. And here see VM3 1.55 volt, 2 volt approximately for LED. Okay, LED is on there. So let us see VM2 5 volt output of the microcontroller 5 volt. See the current. It's approximately 10 milliampere, 10.45 milliampere. Okay, so okay. Now let us see the next circuit. So this is a PMOS DC circuit. Here the only difference is the VGS should be negative to turn on the MOSFET. The threshold voltage in a negative volt region. Okay. So here again from the equation I can derive this resistance. VDD equal to IDRD. Okay, this is 0. So when it is turned on, it acts in the triode region. So this is a voltage in a triangular wave generator. Okay. Okay. So now let's see the circuit simulation. So this is a PMOS circuit, PMOS DC circuit. So let's see the waveform. Oscilloscope. So again, this is just like a square wave as we seen in the first circuit. Okay, 5 volt. And let's see the input waveform. So this is the input waveform. So here it is a inverse of the earlier case. That is in the NMOS DC circuit. Okay, so when it goes below 3.5, negative 3.5, that is at this point it is 1.5, approximately 1.5. So at that time the VGS voltage is negative 3.5. So it reaches a threshold region. So threshold voltage. So as it increases above 3 minus 3.5 to minus 5, the PMOS get turned on. So this is on condition. This is on condition. This is off condition. Okay. So you have to here 5 minus this voltage. Okay. 5 minus triangle wave. That is the circuit here. Okay. So okay. So here it will be high. Okay. It will be high. This is a turn on. So there's a fast switching. So it turns on quickly. On off to on goes rapidly, and on to off quickly. Okay. So now let us see the next circuit. So this is NMOS source follower. So MOSFET source follower. So here just like in BJT, the input is connected. Just in BJT emitter follower, the input is connected to gate, or in BJT it will be connected to base, and you will be taking the output from emitter. So here it will be taken from source. Okay, so and the NMOS that lies in the saturation region. So here the condition is VDS is greater than or equal to VGS minus VT, or the overdrive voltage. VGS is greater than or equal to VDS is greater than or equal to VGS minus VT. Okay, and there will be some voltage here, and you'll be seeing in the simulation there will be some voltage VDS, so that shows that it is in the saturation region. Okay, so this is a NMOS source follower circuit. So here the condition is it lies in the earlier I told it lies in the saturation region. So there is some VDS voltage. So the equation for ID is this one, half mu n C of W by L, that is K, into VGS minus VT the whole square. Okay, like that we can find the ID drain current here. So let us see the voltage of the multimeter. Voltage of the multimeter. Okay, VM4. So there is some voltage here, that is 3.15 volt VDS, and let us take here VM1 1.85. This is the output voltage. VM2 VM2 we get it. It's 5 volt as the input gate voltage, and VM3 3.15. Okay, you can see the current here, 1.85 milliampere. This in current. It's a drain current here. Okay, so that's it. So now let's take here it only difference is the ID is K into VGS minus VT the whole square, unlike in the triode region. So here it is in the saturation region. Okay, here if the condition is satisfied, VDS is greater than or equal to VGS minus VT. That's overdrive voltage. VDS is greater than or equal to overdrive voltage. Okay, so now let's see the next circuit. So another application is NMOS analog switch. It has many applications as given here. So here there is an input signal here. Will be directly connected to the drain, and the output resistor is connected to source, and then we'll give some voltage here to turn on the MOSFET. So when it is turned on, the switch will be closed, and the channel, because the channel is formed, and it acts as a closed switch. The resistance here will be zero. There will be zero drop here. So that shows that it will be in the triode region. So the condition is VDS, VDS is less than VGS minus VT. That's a overdrive voltage. VDS is less than VGS minus VT. Okay. And the first application is used in sample and hold circuit in ADC. See here, there will be input signal here, and will be this will be connected to a port of a microcontroller or FPGA. And when we give high voltage here at the gate, this will be closed, and here there will be a capacitor here, and that will be transferred to the capacitor. The voltage will be transferred to the capacitor, then it will be turned off, and that capacitor will be holding that voltage, and further processing will take place here. Okay, so and next application is analog mux. So here there will be many transistors at the input side, and we can select any one of the transistors. Will be turning on any one of the transistors, and that will be connected to one output. So like that we can route one many channel to one channel. That is a mux operation. Okay, and next is switched capacitor filters, where where the MOSFET and the capacitor will be connected, and it will be rapidly switching. The gate will be turned on and off quickly, rapidly, and that will be act as a resistor here. And the equation for that is 1 by FCC, the frequency of the waveform, square pulse train, or square waveform for the microcontroller. 1 by FCC, that's a value of the resistance, and that will be this MOSFET will be acting as a resistor here when it will be fastly switching, and that will be used in some filters, low pass filters, high pass filters, like that. Okay, that's the main application there. And next is AV signal routing, for example for home theater and set-top box and all. The audio signal routing will be placed with the analog switch here, and when one of the input can be connected to output through this switch, this MOSFET switch. And next is CMOS transmission gate, where this is the NMOS analog switch. So and PMOS will be connected here at the drain and source, and that will be the gate of the PMOS and NMOS will be connected to the same voltage, and like that it will be switching and the input synchronous in, that is positive to negative voltage will be transferred to the source here. And in this case, only the positive portion of the signal will be transferred to the load. In CMOS transmission gate, as there is also PMOS also, the negative portion also will be transferred to the load. Okay, so now let us see the simulation circuit. So this is the analog switch circuit. So here I give the triangular, sinusoidal signal here. So let us see when the gate voltage is 6 and the load is a resistive load 1K. Okay, so now let's see the waveforms. So these are output waveform. See here, this is output waveform. Let's see the input waveform. It is the same as the input waveform. See here. So when I give turn off the VGS, that is a gate voltage here. Let us see the output goes low. See, the output is dead here. Okay, let us uh, slowly increase the voltage 2 volt. Again it is low. Let's keep it 4. Some voltage is coming. So this can be controlled from a microcontroller or a FPGA chip. Okay, so if you give a 0 volt here, this will be turned off, the switch will be turned off, and if you give 6 volt here, this will be turned on. Okay, that is the logic. Okay, so now let us see the next circuit. This NMOS has a variable resistor, the MOSFET has a variable resistor, and in this application, the MOSFET lies in the triode region. And the triode region, you can see it can act as a variable resistor before the pinch off starts. Okay. Okay, so here the condition is VDS is less than VGS minus VT. That is VDS is less than the outdrive voltage. Here I given the gate voltage here. The 9 volt is connected to a port, and the voltage can be slightly varied. Okay, and this acts as a potential inverter here, and here there will be an input sense on signal. Okay, and when the resistance of this VDS, that is the drain to source resistance is changed, that's the channel resistance is changed, and the voltage will be changed, and this can be viewed in the voltmeter on the oscilloscope. Okay, and the application is automatic gain control circuit, and this HG circuits are used in audio receivers, radio receivers, to keep the output signal volume strength constant even if the input signal fluctuates widely. Okay, so if the incoming signal gets too loud, a feedback circuit automatically increases or decreases the voltage to the MOSFET gate, and this changes the MOSFET resistor, which is given at the feedback. Okay, so then the gain remains constant. Okay, like that. Okay, and next is voltage control filters, and a standard low pass filter uses a resistor and capacitor, where the cutoff frequency is determined by Fc is equal to 1 by 2 pi Rc. So by replacing a physical resistor with a MOSFET, and the voltage is varied, the gate voltage is varied, so the cutoff frequency can be changed. Okay, except the resistance is changed, so cutoff frequency will be changed. So like that we can change the cutoff frequency without changing the any port of in potentiometer or any variable resistor, like that, any physical variable resistor. We can change the cutoff frequency electronically. Okay, so next application is voltage control oscillators. The frequency of an oscillator depends on how fast a capacitor charges and discharges through a resistor. Using a MOSFET as that resistor allows an external control voltage to change the charging speed, so thereby controlling the oscillation frequency. Again, it can be controlled electronically. So here all the applications, the common purpose is can be all the resistance can be controlled electronically. Okay, and next application is electronic load. So when testing big power supplies, batteries or solar panels, we need a way to simulate different load conditions without sapping out massive physical resistors. Okay, without changing physical very big physical resistor, we can change the variable load electronically by changing the voltage at the gate. Okay, and next last application is soft start and inrush current limiting. Okay, so when large power supply or motors are turned on, they can draw a massive spike of inrush current that can damage components or trip breakers. Okay, so the inrush current, the starting current, can be very dangerous in such applications. So a MOSFET is placed in the power path, and when turn on, the gate voltage is slowly ramped by a RC circuit. So MOSFET starts with a very high resistance, so limiting the initial current spike, and smoothly transitions into a near zero resistance state as it fully turns on. Okay, so at the starting current, the the MOSFET can be given high voltage, or the resistance can be made high by giving varying the gate voltage, and after that it can be slowly made to zero. Okay, by varying the gate voltage. So that is also done electronically here, no physical connection here, all are electronically done. So that is the main advantage and use of MOSFET other than BJT. So these two are the last two applications are mainly a great advantage for MOSFET, that is the analog switch and variable resistor. Okay, this cannot be done by a BJT. Okay, so now let us see the simulation circuit. So this is a variable resistor circuit. So here I given a input drain signal of 1 volt one volt amplitude sinusoid signal with 1 volt DC voltage, because it will be taking only positive side of the voltage here. Okay, so here let us see the waveform. So this is VM1. So this is output. So now it is it is acting as an open circuit. The resistance is very high because VM3 is also 1 volt. So now let us change the potentiometer. See, this is small distortion here. Okay, so let us VM3. I'll just put it down. Okay, small distortion, but the voltage is less. Okay, and now let us see again. Let me change the voltage potentiometer. Okay, 59. Okay, okay. See, now the voltage is very less. That's a small distortion. That's the because of the nonlinear characteristics of the MOSFET. There will be a small distortion here, but we have to keep it in the linear region. So now the voltage is very less. Okay. So see that one. So again, it is much clear. There is small distortion here. That is because of the nonlinear characteristics of the MOSFET. At the triode, it is a nonlinear portion of the MOSFET. Okay. So that's it. Okay. So this is simulation. Now this potential is the voltage is low here. Okay. So that's it. So that's it, guys. That's the end of the lecture. Okay, we have discussed six circuits. 6 different good circuits. Okay, so that's it. We have seen all the simulations. Okay, so now please like and share the video and subscribe the channel. Okay, and if you have any doubt, mail me to chanch48 at gmail.com. So thank you for patiently listening the lecture. Okay, thank you.